Probably have seen a few videos on asteroid 2024 YR4, which has a greater than 2% chance of hitting Earth. I'm not going to talk about how we found it. In this video, I just want to focus on how we determine the orbit given a set of measurements. We will cover what these measurements are and how these measurements get converted into an orbit. My name is Jorge, I'm a physicist, and these are techniques that I actually use at work in order to determine the orbits of satellites and rockets around the Earth. Below me is a little video that shows the actual track of this asteroid against the background of the stars. Now this track, this little blob you see going across the screen, is a measurement because that screen is taken from a telescope that's pointed somewhere in the sky and you know where you're pointed. So now we can take where that blob is located inside the field of view of the telescope along with where the telescope is pointed to generate a vector or a line that emanates from the telescope and goes to the asteroid. And this is the measurement. But we have to be careful. This line doesn't have a length. It's of unit length. All we know is that we're pointed in a certain direction. And these are the measurements. We call them pointing vectors. They emanate from the observer to the object. And we want to take a sequence of these and process them in a way to generate the trajectory. Now we have a set of measurements, these pointing vectors. We need to make an orbit out of them. Well, how do we do this? Well, we do this through a gravitational model. The gravitational model allows us to take an initial position and velocity of this asteroid, which we have to guess at, and fly it forward. Namely, fly it through the time at which we make the measurements. In doing so, we can actually make predicted measurements using our model and that initial position and velocity and compare them to the actual measurements. And this is the orbit determination process. It's basically trying to minimize that difference by guessing different initial position and velocities. By minimizing the difference between our predicted pointing vectors and the ones we measure, we can arrive at a position and velocity that is an orbit that's consistent with those measurements. And now we can take this position and velocity and propagate it forward 10 years, 8 years, however far we want into the future. When we talk about probabilities, we need to talk about statistics. And when we talk about statistics, we need to talk about the quality of our measurements. So all of these pointing vectors are not actually just some line that points in space. They're actually little cones because there's always some uncertainty. When we point our telescope into the sky, we don't know exactly where it's pointed, but we might know to within a few arc seconds. Just like we converted the pointing vectors into trajectory, we can convert the errors in these pointing vectors into errors in the orbit. These get encoded as errors in the initial position and velocity that we propagate forward. We call this the covariance on position and velocity. And just like you can take that initial state and propagate it forward, you can take that covariance, that initial covariance, and propagate it forward. And this is a thing that will grow over time if no more measurements are incoming. We have taken a set of pointing vectors with associated errors and converted them into an orbit, which is encoded as a position and velocity along with an error on that position and velocity. Given this, we are now armed to start calculating probabilities. And the way I think is easiest to do this is through a Monte Carlo method. There's uncertainty around position and velocity, so we can just make random draws within that uncertainty ellipse. And for every random draw, we just fly a trajectory. Do this billions of times and count the number of trajectories that actually hit the Earth. That number divided by the total number of trajectories that you drew gives you a probability of hit. This is a Monte Carlo method. There are other methods, but I always like Monte Carlo methods because they're just kind of brute force and they work. When we are differencing the measured pointing vectors and the predicted pointing vectors, and there's an error in those, there's a very nice function we can use called chi-squared. Chi-squared is nice because there's a lot of theory behind it. We know how to interpret its value. Not only that, our chi-squared here is an explicit function of the initial states, the position and velocity of that orbit, because that is what is used with our gravitational model to create all of the predicted measurements that we will compare to the actual measurements. This is now just a nonlinear optimization problem. You can use calculus to solve it for certain types of functions. In our case, you have to use numerical methods. But either way, what we're trying to do is minimize chi-squared. And a beautiful thing about chi-squared is that you can actually go in and do the derivatives of this thing with respect to those initial states. And if you do two of them, you basically get a curvature. And this curvature is really something we call the Fisher information matrix. And if you take that thing and invert it, you get your covariance. So if you use chi-squared, you're able to do the minimization you need in order to fine-tune that position and velocity to give you the best match to the measurements, but it also gives you a recipe for calculating that covariance. And as we talked about earlier, you need that covariance in order to be able to make draws on initial positions and velocities to fly to see if they hit the Earth in order to calculate these probabilities. So chi-squared optimization is something I use a lot. It's extremely powerful. We call this a batch method. You're putting a bunch of measurements in a bucket and you're processing them once. You can also use filters. That is, you given some initial state that you've already gotten from a batch process, by the way. But if you already have a state in an orbit and new measurements start coming in, you don't have to throw all of these new measurements in a bucket with the old measurements and do this whole process again. What you can do is take your current best state estimate and condition it on that incoming new measurement. And this is done in a method that's very similar to talked about before. We're going to make a predicted measurement. We're going to compare it to the actual measurement coming in, but we'll do this using something like a Kalman filter. If you know any electrical engineers in your life, ask them about Kalman filtering. It's super useful, widely used. I use extended Kalman filters, which allow to do nonlinear systems all the time. In the process of calculating this probability of impact, we will see that there's a wild divergence of these trajectories as we sample different initial positions and velocities. And if you go in and analyze it, you'll see that this divergence is mostly due to velocity errors. And so any tracking system is looking to really beat down these velocity errors so that when we make our forward predictions, we have kind of like the smallest possible spread. Now, there's 3 ways to beat down these errors. One is just use a new type of device like a radar. We'll talk about that in a minute. The second is just get more measurements. The more measurements I have coming in from any sensor, I'll get these errors in the estimated state. They'll drop as like 1 over square root of n. And the third way is to add viewing angle diversity, which means look at this asteroid from different views. Use a telescope on one side of the Earth. Use a telescope at Lagrange point 1 or 2. This viewing diversity, with it brings implicit position information by virtue of triangulation. If I have 2 telescopes, one looking this way, one looking this way at the same object, those pointing vectors meet at a point in space, and this gives you a position. So you can have passive measurements yield position information through something called triangulation. Radars are nice because you can directly measure range, and through Doppler shift, you can actually get a projected velocity measurement. Both of these are great at reducing your velocity errors. Key topics we've covered: chi-squared optimization, pointing vectors, orbit determination, position velocity, covariance, covariance growth, Kalman filters, specifically extended Kalman filters. If you're more interested in any of this, go look at any of those terms or hit me in the comments. Thank you all for being here. We'll keep you all posted on this asteroid. After spring, it's going to go black in the sense it'll be getting a little bit too far away from Earth for us to track it. And so we're not going to get any real refinement off of this probability unless they go back to the measurements that have already been collected and find some new way to process them or find some error in the previous processing. Thank you all for being here. Be well.